Okay, so I got the solar panel hooked up. I built the entire circuit, and I'm going to probe the input first. So ground, cell in. Cell's generating 3.9 volts. Output voltage is 3.65 right now. That's the cell voltage. This is the output voltage, and let's see what's on the battery terminal. 3.65. So, for some reason, it's outputting a very low voltage, lower than what's going into the cell. So seems like I'm not getting any boost conversion. Okay, so maybe this just won't run without the battery attached. So now, we have the battery attached. Probing cell voltage, 3.8. Output voltage, 3.8. Alright, let's turn up the brightness again. On. .92, output voltage 3.81, and battery voltage 3.8. So now I'm going to set this to its lowest current range. This is supposed to be 20 microamps, but I don't know if we'll succeed in getting that. So just disconnected the negative lead on the battery. Let's see what kind of current we get. So I'm having the negative on the negative lead of the battery, and positive on the positive. 0.6 microamps. Now let me turn off the light. 0.6. Let me get my actually good light, my actually powerful light, and we'll see what happens. Okay, I got a very powerful headlamp, and I'm going to shine it on directly on the solar panel. See if we get any change. So we're at 0.6. Oh, I went over current. Let's go up a scale. There we go. 42 microamps. So it looks like we're going to need some serious brightness for this to operate. Alright, let's go to the 20 milliamp range. I think must not be making very good contact for it to bounce around like that. Either that or it's got to do with the pulsed nature of the charger. There we go, it was bad contact. So I am charging at 0.5 milliamp in this light. Okay, so it's been charging for 12 hours now. I'm just going to go ahead and measure the battery voltage. You can see it's increased by about 20 millivolts. That's actually not bad because our average charge current was 300 microamps, and this is a 100 milliamp hour battery, so in theory to fully charge at that rate it would take about 500 hours, so 10 hours for 20 millivolts is not that ridiculous. Now I want to go ahead and show you the voltage on the solar cell. So you can see the solar power section. It's pretty screwed up. I'll point out a couple of things before you measure it, if I can here. So you can see the solar cells attached on the red wires. Here, because I didn't have the 0402s, we have these 4.7 0805 mega resistors. And there's a couple of bodge wires. This one, I forgot this trace here, where it goes to the inductor to the V-in. This one got torn off when I was trying to rework this capacitor, because I thought it was too close to this one, and that, you know, this terminal to this terminal. This capacitor is important because it has to be low leakage, otherwise you get this problem I'll show you in a second. And now it's working better now that I moved it a little bit, but I think because of the flux residue and other things, it's still got too much of an electrical path around the board, and it's having some issues. And here's our C store. Here's where the battery voltage comes out this way to the battery, and control resistors for controlling charge voltage and stuff. So now let's look at the cell output voltage. You can see 2.8. Now what's interesting about this IC is it has a 16-second cycle. That's the capacitor I was just mentioning. Right there, you saw a jump up to 3.5 or some number close to that. That was its 16-second period, the end of it, where it unloads the solar cell and stores the voltage divided by these two resistors, so 73% approximately, and it tries to load it down to that. Now the problem is there's so much leakage, you can see it's slowly dropping. That's because the capacitor is leaking and the comparator inside there is lowering the average voltage it takes. So that's part of the MPPT algorithm. It jumps up to about 73%, and you can see it seems to drop about a millivolt or so every half second. So it loses maybe 20 millivolts over the 16-second time period, I would think. Maybe 20 to 4, so 93, so 0.93. And by the end of its cycle, it will reach so it loses about 200 millivolts. So that's not terrible. But now, let's watch the current flowing into the battery under these conditions. So this right here is about 5,000 lumens. Let me double check that measurement with my phone. I don't have a proper lumen meter, so I'm going to use my phone real quick. I'll see what it measures. This is a Galaxy S6 Active for reference. And I'm going to use the GPS status app to get the lux, the amount of lux according to it. Now I'm putting it right next to the solar cell, and it says 2,100 lux. Let me put it a little closer and in front. 4,000. So it's getting somewhere below 4,000 lux according to the phone. That's like our high estimate, so putting in a little room for error. Now I'm going to measure the battery current real quick here. Alright, so we're getting 120 microamps. Right, so I think a lot of my problem last night, where I was seeing it jump a huge amount, was just that there was still too much isopropyl alcohol on there. So I had the flux residue, cleaned it without the isopropyl alcohol, and that really increased the leakage current. Now that it's had a night to dry out, it's working much better. I still think it would be better if these boards were, say, done professionally, solder paste, single shot, instead of botched together like this. But we actually have relatively low leakage current, and you can see we're only changing by a few microamps. So let's watch it and see how it cycles. You'll see it jumps to 0 briefly. That's when it cuts off the power. So 123 microamps, that's the high part of the cycle. There we go. So about 8 microamps. So we're averaging around 120. Now, in this case, it would take about 3 times longer. The solar cell, when it's directly under the light, it's charging at 300 microamps approximately. That's what I had. Let me move the light so it's right over the solar cell so we can see that for comparison. See if there's actually a difference. There should be. Last night I was getting 300. Oh, wow, yeah. So that's 400 microamps. That's way more power. So this is 40 times what you would need. Alright, I'm going to take this upstairs. I'm going to try this in a couple spots where the cats like to hang out. We'll see how that works out. So, there's one kitty. There's another kitty. And here's one of the spots the kitties like to hang out. Kitty, you can't hang out here right now. We're doing some video. Alright, so I'm going to try and get this all in one shot. So you can see we got full sun. This is a direct sun spot we're testing. Then I'm going to go test the spot inside the house just to see kind of ambient. Okay, 500. So we're looking at 500 microamps. Oh, Yeah, I knew this couldn't last. Alright, I'll put the meter somewhere else, and we'll just watch the meter. You already seen the setup. Okay. So you can see, we're actually getting interference from the tree right now. The tree is getting all up in the way. This is actually not direct sunlight. This is cleared by some leaves slightly. Well, you can see we're bouncing around 1, 3, 4. It looks like we're peaking around 3 milliamps. So this is steady. That tree, the wind blew the tree out of the way, and we're getting around 2 milliamps. Of course, this is a terrible meter, so these are just rough estimates. Yeah, okay, so a lot of this is also the leakage current. It looks like at these higher currents, it jumps around a lot more. We're getting between 3 and 2 milliamps in one of the direct sun spots that the cats like to hang out in. So now I'm going to try out one other spot. Yeah. Okay, you can see how much the cats like this spot. They just jump right over it. I'm going to put this on the microamp range because I know we didn't get milliamps. Alright, ambient light. We are actually charging at 24 microamps. So not as good as 31. Alright, let me set this to the lower range. So 31, lower range. So we'll let it cycle. 32 microamps. So that's 3 times what the system needs to run in ambient lighting. Just during the day. Sunny day though. So that's the thing to remember. This is a sunny day. So this is, as long as the cats are in the house, so I dropped to 17. So we'll say 20. So the cat's got to spend like 12 hours in ambient indoor lighting. It's just barely enough to charge it at twice the power. Now it might work better because obviously we have seen you can draw 32 milliamps if the MPPT algorithm is working properly. So hopefully on the final board we'll have less leakage and the MPPT will work better, and that should allow us to charge at 3 times the rate. So as long as you have, on a sunny day, you got 8 hours of light, as long as the cats aren't hiding under beds all the time, it should be able to charge the collar fully from what it used during the day.